Hello everyone. Today I'm excited to present our research on dynamic AI driven task offloading and edge computing. I'm Kartik Sharma from City University of Hong Kong, and my teammate Dylan and I have been working on developing a novel approach to optimize task execution in edge computing environments. Edge computing has emerged as a crucial paradigm for reducing latency and improving efficiency in distributed systems by processing data closer to its source. However, deciding whether to execute tasks locally on edge devices or offload them to the cloud servers presents a significant challenge, especially in environments with changing conditions. Our research introduces a reinforcement learning based approach that dynamically adapts to these conditions in real time, outperforming traditional methods across key matrices. Let me explain our system model. We are working with edge devices with limited computational capabilities and battery life, cloud servers with high computational power but accessed through potentially unreliable networks, tasks with varying computational complexities, data size, and deadline, network conditions that fluctuate over time. The challenge is deciding for each task whether to execute locally or offload to the cloud to optimize multiple objectives simultaneously that are minimizing execution time, reducing energy consumption, controlling monetary cost, and meeting task deadlines. Traditional approaches use static rule, but these fail to adapt to dynamic conditions. That's where our reinforcement learning solution comes in. We formulated the task offloading problem as a Markov decision process with a state space that captures task characteristics, network conditions, and device status. A binary action, execute locally or offload to the cloud. A multiple objective reward function, balancing time, energy cost, and deadline constraints. A solution uses a deep queue network architecture with an input layer capturing 6 state variables, 2 hidden layers with 24 neurons each, an output layer predicting the value of each action. As I am demonstrating here, the agent learns through experience, replay, and exploration, continuously improving its offloading decisions as it encounters different scenarios. We evaluated our approach against 3 baseline heuristic methods: a threshold-based approach that offloads based on task complexity, an energy-aware approach that prioritizes battery conservation, a latency-aware approach focused on minimizing execution time. This visualization demonstrates the decision boundaries of our RL agent across different task complexities and network conditions. It learns a more nuanced policy compared to fixed rule of heuristic approaches. The performance comparison dashboard showing our RL agent achieved 23% lower execution time compared to the threshold heuristics, 31% lower energy consumption compared to latency aware heuristic, 15% lower cloud cost compared to energy aware approach, and crucially 42% lower deadline violation rate compared to all heuristics. Let me quickly walk you through our implementation. Our software is built with Python and TensorFlow, providing the core RL algorithm implementation, simulation environment, modeling edge devices, service task, and network conditions, visualization tool for performing analysis. Here you can see the algorithms in action, making real-time decision as task arise and network condition change. The environment simulates realistic edge computing scenarios with variable task complexities, data sizes, deadlines, and network latency. What particularly noteworthy is how the RL agent balances multiple competing objectives without requiring manual tuning, adapting its strategy based on the specific condition it encounters. In conclusion, our research has demonstrated that reinforcement learning provides a powerful approach to task offloading in edge computing environments. It outperforms traditional heuristic by adapting to changing conditions and balancing multiple objectives. Future direction for this work includes extending to multi-device collaborative offloading, implementing partial offloading capabilities, exploring federated learning approaches for privacy preservation, testing on real-world edge computing hardware. We believe this research contributes valuable insight to the field of edge computing and demonstrates the potential of AI-driven approaches for optimizing distributed systems. Thank you for your attention.